Well, hello everybody. Welcome to another day of class. If you recall from last Thursday, I know it's been a while, but we were talking about proofs. And on Thursday we did proof by contradiction. So up to this point what we've done is we've done a direct proof, we've done a contrapositive proof, and we've done a proof by contradiction. Most of the things we've tried to prove though have been conditional statements, that is, if something, then something. And so we've been trying to prove that using the three techniques we have. Today what we're going to do is we're going to focus on non-conditional statements. So we're going to look at things that aren't if-then statements. So they're going to be statements that just say something, or there's going to be different types of options than just if-then. The first example I wanted to look at is, as opposed to an if-then, we can do an if and only if. So what's the difference between if-then and if and only if? Well, if we do if this then that, we get to assume P and we have to show Q. Whereas if we have to do an if and only if, what this really means is that we actually have an if then in both directions. So if I look at this one, I'm saying that an integer n is odd if and only if n squared is odd. So I'm actually making two claims here. The first claim is if n is odd, then n squared is odd. And the second claim is if n squared is odd, then n is odd. Now, as far as doing these refer back to just, okay, well, if I focus on this piece, it's just going to be a conditional statement. We're going to prove this. We could do this one directly. If n is odd, it's congruent to 1 mod 2. Therefore, n squared is congruent to 1 times 1 is 1 mod 2. And so we could do this, just assume this, show this, and that works out like ones we've done before. This one, again, it's an if-then statement, so it falls back on our other proofs. I think this one would be easiest as a contrapositive. We would assume n is even and then show n squared is even, which if n is even, then n is congruent to 0 mod 2. So n squared is congruent to 0 times 0 is 0 mod 2. So I didn't try to set this up as difficult proofs. I just want to say if we have an if and only if. So instead of just an if then, an if and only if really means that I have two proofs. I have to do this direction and I have to do that direction. Now, as opposed to an if and only if, what I can also have is equivalent statements. So that is, in this case, I have let n be an integer, then the following are equivalent. So I have 1, n is even, 2, n is congruent to 0 mod 2, 3, n squared is congruent to 0 mod 2, and 4, n squared is even. Now, if I say that these statements are equivalent, what I'm really saying is that each one, if I replace 1 and 2, I would say 1 if and only if 2, 1 if and only if 3, 1 if and only if 4, 2 if and only if 3, 3 if and only if 4. And so we have that if I pick any two of them at a time, it's going to cause an if and only if statement. Therefore, each of those things is, again, two statements because it's if 1 then 2 and if 2 then 1. So what I get here is, if I wanted to show this according to my previous technique of just show both directions, I'd have to go through every pair. And since we spent some time counting, if I have 4 things to choose from and I want to pick 4 choose 2, well, 4 choose 2 is going to be 4 factorial over 2 factorial times 2 factorial is going to be 6. So there'd be 6 pairs I'd have to check. Each of those is going to give me 2 proofs. So I'd actually have to do 12 proofs to show all of these are equivalent. And if I want to continue to 5 or 6 or 7, it's just going to become more and more work. And so if we have a following are equivalent, it is a lot of work to try to do it that way. So instead what we're going to do is we're going to think about this in a different way. We're going to say,
Well, if I want to show that everything is equivalent, instead of working through every case where every pair is if and only if, what I could do is start with something and I'll only start with 1 and show 1 implies 2. So I have if 1, then 2. And then I can show 2 implies 3. So if 2, then 3. And then if 3, then 4. And then if 4, then 1. So now I still have to do 1, 2, 3, 4 proofs here. But if I do this, 4 is obviously less than 12. But the idea is I've shown 1 implies 2 implies 3 implies 4 implies 1. So to get 2 implies 1, I would just follow the argument 2 implies 3 implies 4 implies 1. Or that 3 implies 2, well 3 implies 4, which implies 1, which implies 2. So therefore we could follow the path all the way around because it becomes circular, and we get that any pair becomes an if and only if. So we start with one of them and we work our way through. We don't necessarily need to go 1, 2, 3, 4, 1. We could go 1, 3, 2, 4, 1. We just have to make sure that we get a loop that contains all of the equivalent statements. So that will save us, again, some work. All right, let's actually do this one. So if I have to do 1 implies 2, what I said is n is even. So assume n is even. Then what do I have to show is that n is congruent to 0 mod 2. And so just as a point, this is actually one of the equivalent statements that we've already proven, is that n is even is equivalent to saying n is congruent to 0 mod 2. So we can refer back to an earlier proof, so we don't actually even have to write anything here. We just say, oh, n is even is the same thing as n is congruent to 0 mod 2. To show 2 implies 3, we just assume n is congruent to 0 mod 2, and I want to show n squared is congruent to 0 mod 2. Well, then I would say n squared is congruent to 0 times 0 mod 2 is 0 mod 2. Hence, we get 2 implies 3. And then 3 implies 4 is just, we assume n squared is congruent to 0 mod 2. And then we show, and again, as we did for 1 to 2, we know that these two are already equivalent because we've shown that before. So if n squared is congruent to 0 mod 2, that means n squared is even. The last thing I have to do is to show 4 implies 1, so I get to assume n squared is even, and I have to show n is even. But in this case, when I'm actually showing if n squared is even, then n is even, this would actually work better as a proof by contrapositive. So that is, I'm going to assume the negation of n is even, and I'm going to say assume n is odd. And I have to show n squared is odd. And again, n is odd means n is congruent to 1 mod 2. So therefore, n squared is congruent to 1 times 1 mod 2, which is 1 mod 2. So as I look at those, these ones aren't meant to be difficult proofs. They're things we've actually done before, so if you want to go back and look at all the details, you can do that in earlier ones. The idea is just instead of having just one if-then, we're trying to show that 4 things are equivalent. So we're going to show this type of pattern where 1 implies 2 implies 3 implies 4 implies 1. So that I only have 4 proofs to do to show that all of these things are equivalent, instead of having to do every pair together, showing each one's equivalent. All right. So now, as far as new things,
the if and only if and the equivalent statement things aren't all that new. They're just a little bit more general case of what we've been doing. So you just have to go both directions, and or you have to follow through on all these. So can you do them in any order in either direction? Well, you have to be careful with the ordering. Is you can do them in any order. So you can do 4 implies 3 implies 2 implies 1 implies 4, but you have to make sure you get a loop when you're done. So I can't do 1 implies 2 implies 4, and then 3 implies 4, because I don't get a loop then. I get 1 goes to 2 goes to 4, and 3 goes to 4, but there's no way to show from that loop that 2 goes to 3. I'll go back up to the chalkboard and just show you what I'm talking about. Here we can get from any one to any other one going through this loop. But if I did some proof like this, 1 implies 2 implies 4, and I do 3 implies 4, well, there's no way to get from 2 to 3 because these are directed proofs, so I can't go backwards. So what I would have to do then is, well, I'd have to do something like 4 implies 3, and then I can get from 2 to 3, back up to 4, to 1, to 2. And so as long as in the end what you get is something that you can write out, and I can start from any other one and follow directionally to get any other one, then that is fine. You just have to make sure that you can do that. But if you want to start at 4 or start at 3 or start at 2, that doesn't matter. You just have to make sure that in the end, if I follow the arrows, I can get from any one of them to any other one of them. Does that help? So the last one, when we showed 4 implies 1, we used a proof by contrapositive, meaning that instead of assuming the if part and showing the then part, we assumed the not the then part and showed the not the if part. That's a contrapositive. If we wanted to do contradiction, we're going to assume the negation, and then based on the negation, we have to find a false statement. Now, you could have used a proof by contradiction in the last one as well, but I decided to go with contrapositive. All right, I hope that's helpful. Now, here's what I was getting to, is that those are kind of generalizations of if-thens. They're kind of generalizations of conditional statements that we have been working with. However, for this one, what we have is there exists an even prime number. So there is no if part, there is no then part. We just have to show there exists a prime even number. So to go back, contrapositive will end up true, yes. So contrapositive will be assume something, and then you get a true statement. Whereas with a contradiction, you're going to end up with something that is clearly false. Therefore, your original assumption is false. Therefore, the theorem you were trying to prove, which was the opposite of what you assumed, would be true. All right. So now back to this one, I'm just trying to point out that this is called an existence proof. So I have to show there exists an even prime number. And the point here is I don't assume something and then show something. For an existence proof, I just have to show that this exists. Now, for most of these existence proofs, that just means come up with an example. So, for prime numbers, can I think of an even prime number? Maybe you guys can help me out. Is there an even prime number that you can think of? Two. Very good. You guys got it. So 2 is both even because it's divisible by 2, and it's prime because it's only divisible by 1 in itself. Therefore, there is an even prime number because we've given an example. And a lot of times that's what existence proofs look like, is you just find an example, therefore it exists. Now I don't have it written up here, but we could also do a uniqueness proof. What would uniqueness mean? we could say not just there exists an even prime, but there is a unique even prime. And a uniqueness proof would mean that, well, there's only one of them. So exist means there's at least one, and uniqueness means there's no more than one. So to show uniqueness, I have to show that if there were two of them, they would actually have to be the same. So if I go up to the board here, what I'm going to say is, assume that A and B are, in this case, even primes, but in general it could be anything. A and B are anything. Then A is equal to B. So what I'm saying here is I assume that I have two of them. I showed that they have to be the same. That means that if I had any other ones, they'd have to be the same. So if I have anything that satisfies this property, namely being an even prime, it has to be equal to the original one that I found, so there can be only one. So this is how we do it in uniqueness proof. So you assume that we have two, and we have to show that they're equal. All right, so for this one, I already know that 2 is an even prime. So let's assume that I have A and 2 are even primes. What I want to be able to do is show that, in this case, A is equal to 2. So therefore, if I had any even prime, all of them have to be equal to 2, so 2 is the unique even prime. So that's the argument we're using here. All right. So, how would we do that? Well, what we get is A and 2 are both even primes, so A is even. But since A is even, 2 divides A. However, we know that A is prime, and prime means that it's only divisible by itself and 1. So A is only divisible by itself and 1. Since 2 is not equal to 1, A has to be equal to 2. Because we found a divisor of A, but A is prime, this divisor is not 1, therefore A has to be equal to that number, otherwise it wouldn't be prime. So since A is even and 2 divides A has to be equal to 2. So the only even prime would indeed be 2. Does that make sense to everyone? All right. So that one was a fairly straightforward one where we just found the answer and then we said, oh, well, if we had any other ones, it had to be equal to 2 anyway. And so we followed through the definitions to get that. This one's going to be a little bit more complicated. And what we're going to say is let A be a non-empty finite set of real numbers. Then, I should say not of real numbers, of integers. Let A be a non-empty, finite set of real numbers. Sorry, I'm making sure I'm reading that correctly. Let A be a non-empty finite set of real numbers. Then A has a unique smallest element. So has a smallest element means that we have an existence proof here. And unique smallest elements means we have a uniqueness proof here. So what we have to do is we have to find the smallest element and show that any other such smallest element would have to be equal to it. So we have two things to do here. We have to find the smallest element and we have to show that it would be unique. All right. I'm actually going to start off with uniqueness here. So I can show something's unique even if I don't know it exists, because unique means there's at most one. So if we have 0, that answer would still be considered unique. It's just you would have no answer. So what we're going to do is we're going to assume that we have two smallest elements, and we're going to show they're the same thing. So let A be a non-empty finite set of real numbers. Also, let A and B be the minimum of the set or the smallest element in the set. So I'm going to consider A and B to be the smallest elements. Since I want to show uniqueness, my goal is to show A is equal to B. Alright, now before we get into this, we do have to talk about definitions. Is what is the smallest element of a set or the minimum of a set? Well, what this means is that A is the smallest element of the set if A is less than or equal to, let's say, X for all X in A, and A is in A. So to be the smallest element, it has to be in the set, and it has to be less than or equal to every element in the set. So now, since A is the smallest element of A, and B is the smallest element, that means B is an element of A. Hence, A is less than or equal to B, since B is an element of A. So this is an element of A, therefore little a has to be less than or equal to it, because it is the smallest element. By the same reasoning, since B is the smallest element, it has to be less than or equal to A, since A is in A. Hence, what I get is that A is less than or equal to B is less than or equal to A. So what this means is that, well, notice that B can't be different than A, because if B was strictly bigger than A, that'd be a contradiction. If B was strictly smaller than A, that'd be a contradiction here. So this, if B was smaller, it'd be a contradiction here. If it was bigger, it'd be a contradiction here. So the only way this is possible is if A is equal to B. Hence, if I can show A is less than or equal to B is less than or equal to A, that means A is equal to B. So therefore, if A has the smallest number, then it'll have a unique smallest number. And actually, we didn't even use finite set here or non-empty. We just said if A was a set, if I have a smallest element, that smallest element will be unique. I can't have two smallest elements of a set of real numbers. Does that make sense to everybody? Any questions on that one? All right. The next thing is we have to show there is a smallest element. So what I'm going to have is the set A. I know that it's a non-empty finite set of real numbers. So I have to show that there is a smallest element. Well, to show there is a smallest element, I have to find the smallest element. Now, I just want to point out here, I don't know anything about A. I don't know what elements are in there or what elements aren't in there. I just know it's some arbitrary finite set. So, if I were to try to directly find it to show that it exists, that actually becomes a difficult proof. It is actually possible. You could actually write out an algorithm to say, suppose I have any finite set, then I'm going to find the smallest by doing some things so that eventually the smallest element will pop out. And I actually have that algorithm written up on the website if you're interested, but it's not an easy thing to do, just out of nowhere. So instead what I'm going to do is I'm actually going to do this one by contradiction. So I'm doing an existence proof by contradiction. So what I'm going to do is assume that A does not have a smallest element. And what I want to do is find some type of contradiction. I don't know what I'm going to end up with, but I'm going to end up with something that has to be false. Now, if A was empty, we'd have nowhere to start, but we know that A is a non-empty set. So since A is not empty, there exists an A sub 0 in A. So there's something in A. And I'm just calling it A0 to give a point to start. So what is the definition of smallest? Is that it is less than or equal to anything else in the set, and it is also in the set. If a set has only one number, then yes, it is both the smallest and the largest element. So if a set had only one element, it would be both the smallest and the largest. Sorry, so I'm just trying to refer back to an example here. Is actually, if we look at calculus, we talked about minimums and maximums of functions. So the smallest would be similar to minimums and maximums. And so if you think about calculus, if you take a constant function, then say the function's always equal to 5, then 5 would be the maximum y value and the minimum y value. And that would occur at a lot of places. But the only y value that is the maximum, or the only y value that's minimum, is 5 itself. So, yes, something can be both the smallest and the largest at the same time, but I can't have two distinct things being the smallest, is what I just proved. So I can't have 2 and 3 both be the smallest, because 2 would be smaller than 3, so that would have to be the smallest. Alright, so just answering a question there. Back to this proof. What I have is, okay, I know A is non-empty, so there's something in A. If there is not a smallest element, that means that A naught is not the smallest element. So that means that it is not less than or equal to everything else in A. So that means that there's something in A which is smaller than this. Then there exists A1 in A with A1 strictly less than A0. That is, this one has to be actually smaller than this one, because otherwise this one could still be the smallest element if they were equal. So I have something in A which is strictly smaller than A naught, because A does not have a smallest element. So I had to have something, and because this can't be the smallest, there has to be something smaller. But what does that mean is, well, A1 can't be the smallest. So there also has to exist an A2, which is less than A1. Because A1 can't be the smallest. But A2 can't be the smallest, so there has to be an A3, and an A4, and an A5, and an A6, and an A dot 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 dot. What does that mean? It means that A0, A1, A2, A sub n is in A for all n in the natural numbers. So that is, I can find A0, so there's some element. I can find a smaller one, then a smaller one, then a smaller one, and I can keep going for every natural number. All right. How many elements did I find here? Well, I found one for every natural number, so how many natural numbers are there? Well, there are infinitely many natural numbers, aren't there? Therefore, I have at least infinitely many numbers in A, so A is infinite. So if there is no smallest element, A must be infinite. However, notice that we assumed A was finite, so can A be both finite and infinite at the same time? Well, no. Hence, this is a contradiction. Therefore, if A is a finite non-empty set, it has to have a smallest element. It has to have a minimum element. The only other option would be it'd be finite or infinite, but we know it's not infinite because that's finite. So any finite set or finite, non-empty finite set of real numbers has to have a minimum element. And that's what we proved here by using a contradiction. So the point here is that we actually did an existence proof without actually finding the smallest element. But what we showed was that if something didn't exist, then we get a contradiction. And so that is another way to do an existence proof, is not just finding it, but saying if it didn't exist, we get a contradiction. So there's another type of proof we can do. And notice again, I'm combining previous techniques with new techniques to get out different types of proofs we can do to find ways to answer new questions, new and interesting things, so that we can then use those to find even more new and interesting things. All right. Now, so let A and B be an n, then there exist integers k and l for which the greatest common divisor of A and B is equal to ak plus bl. The first thing I have to do here is talk about what a greatest common divisor is, because we haven't done that yet. And then, since I'm saying the greatest common divisor here, I'm actually making a claim that that greatest common divisor exists and is unique. And then I'm making a further claim that I can write it as a times an integer plus b times an integer. So this theorem is actually quite involved. There is a lot going on here. And so I'm going to try to break this up into pieces, but I want to say this is where we're going in the end. And the reason why this proof is so helpful is because it becomes very helpful when we're trying to do algebraic calculations. When we're trying to show that other things happen, this is a nice theorem as far as calculation-wise, which will make other things a lot easier. And this is the Chinese remainder theorem. It's restated a little bit, but basically it's equivalent to the Chinese remainder theorem if you need a name for it. And I'm still using this in my abstract algebra class. This has been coming up a lot lately. So it's not the type of thing that goes away. It's something that you end up using over and over again for a lot of different reasons. And so I really like this theorem. So let's go ahead and prove it. All right. So the first thing I need to do is define the greatest common divisor of A and B. So the greatest common divisor of A and B is equal to, say, D, where D divides A and D divides B. That is, D is a common divisor of A and B. Furthermore, if C divides A and C divides B, that is, C is some other common divisor, then C is less than or equal to D. So what we're trying to say here is that I'm going to call the greatest common divisor of A and B is a common divisor of A and B, such that if I find any other common divisors, they're going to be less than or equal to D. So what that means is if I let, say, C be the set of all common divisors, D is the unique greatest element. So what does that mean? It means that to show that this definition is well defined, I have to show that there is a unique greatest element of the set of all common divisors of A and B. All right. Now, in the last theorem, we showed that for a finite non-empty set of real numbers, we had to have a smallest element. But actually, if you follow through the same proof, you can also show that any finite non-empty set of real numbers also has to have a greatest element. Because if it didn't, then we'd have an element, and then we'd have a bigger one, and a bigger one, and we get the same contradiction that would have to be infinite. So what I'm going to do here is, if I can show that C is a non-empty finite set of real numbers, then there has to be a unique greatest element. So I'm trying to outline the proof here is that in order to show that the greatest common divisor always exists, I'm going to show that the set of all common divisors is finite and non-empty. Therefore, there must be a greatest element. All right, with that in mind. So just to remind us, C is the set of divisors of A and B, where A and B we're going to say are integers. So we're working with this for integers, not just general numbers. And so we'd say the greatest common divisor of two integers is the common divisor, which is the biggest. So what I want to do is I want to show that this set is non-empty. So can I think of a number that divides both A and B? All right, Danny, I don't understand. Where'd you get the part from where it says where D divides A and D divides B? So the idea is that if D divides A and D divides B, we're saying it's a common divisor of A and B. And furthermore, if C divides A and C divides B, that means that C is also a common divisor. So what I'm saying is D is a common divisor. And if I take any other common divisor, and C is some other common divisor, that's all that's saying there. So if that's the case, is I can find another common divisor, then my claim is that C must be less than or equal to D. So that's what it means to be the greatest common divisor, is that it is a common divisor. And furthermore, if I have any other common divisors, they have to be less than or equal to D. So it's going to be the biggest one of them. Hopefully that helps. All right. So now I want to show that this is a finite non-empty set. To show that it's non-empty, I have to find something in here, and I'm just going to say note 1 divides A and 1 divides B, because 1 divides any integer. Hence, 1 is in the set of common divisors. Now, the next thing I want to note that is that let's just say x divide A, then A is equal to k times x for some integer k. But if I look at k times x, this is going to be greater than or equal to, because k is greater than or equal to 1, this is going to be greater than or equal to x. So if I multiply x by an integer, if k was 1, I could get x, but if k was any other integer, I should say in absolute value anyway, it's going to be bigger than or equal to x. So if I multiply by -1, I get obviously a smaller number, or -2, I could get a smaller number, but in absolute value anyway, I would multiply it by 1, or 2, or 3, or 4, and so this as an absolute value is going to be bigger than x. Alright, so what I'm trying to point here is that if I have a divisor of A then the absolute value of x is less than or equal to the absolute value of a. Now, what does that mean? Well, it means that if I have a divisor of a, all of the divisors of a have to be a subset of the set of all x such that the absolute value of x is less than or equal to the absolute value of a. So if I have a divisor of a and b, it is a divisor of a. Therefore, the absolute value of that number has to be less than or equal to the absolute value of a. But since this is a subset of this, that means that the cardinality of C, or the size of C, is less than or equal to this. So therefore, the cardinality of C is less than or equal to the cardinality of this set. Well, how many elements are in this set? Well, the thing about the elements in this set, since we could have negatives and take an absolute value, this would be negative A plus 1, negative A plus 2, negative A plus 3, dot, 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 up to 0, then 1, then 2, then 3, all the way up to A. And so what we're going to get here is that this cardinality is 2 times the absolute value of A plus 1. So for example, even if A is 1 million, the idea is that if we take all the values that are less than or equal to 1 million in absolute value, well, we get the natural numbers up to 1 million, and we get the negative numbers down to negative 1 million plus 0. So we get 1 through 1 million, negative 1 through negative 1 million. So that's 2 times 1 million. Plus 0 is 1 more, so we get 2 times that is A. Well, or 2 times that is the absolute value of A plus 1 is the total cardinality of this. But that means the cardinality of this is less than this number. So how do we come up with a subset? Well, what I'm saying is anything that's in here has to be in here. So I said that if something was a common divisor in A and B, it had to divide A. So if it had to divide A, in absolute value, it had to be smaller than A. So therefore, anything that divides A has to be in absolute value less than or equal to the absolute value of A. So if we're going to find a common divisor, it has to satisfy these properties. So it has to be in this set in order to be in this set. And that's how I'm saying that we're coming up with a subset. We are actually going to talk more about subsets and sets in the future when we get to set proofs. We haven't quite got there yet, but I feel like this isn't something I'd ask you to regurgitate at the time, but this is an interesting proof, so I wanted to point out that, well, the idea here is that all of these elements have to look like this. So the point is that if they look like this, I can only have this many of them. And so if if A is 1 million, I can only have 2 million plus 1 divisors. Or if A is 1 billion, I can only have 2 billion plus 1 divisors. Whatever that's going to be, since A is a finite number, that means that 2 times a finite number plus 1 is just going to be finite. So therefore, C has to be finite. Since C is finite and non-empty because 1 is in it, I have a finite non-empty set. Therefore, it has to have a maximum element or greatest element. So therefore, the greatest common divisor of A and B will exist, and it will be unique. Is that all right with everybody? All right. So that is step 1 of our proof. The greatest common divisor of A and B exists and is unique. Well, I still need to do part 2 in that I need to show that it looks like something times A plus something times B. And so I'm going to do this one in a roundabout way as well. And again, this isn't the type of proof I'd expect you to come up with, but I'm trying to demonstrate different proving techniques that you can use throughout different things so that the ones I do give you, you can take some of these techniques and use them. All right. So remember I wanted to show that the greatest common divisor of A and B was equal to A times some integer plus B times some integer. So what I'm going to do is I'm actually going to let's say capital A, be the set of all things of the form A times some integer plus B times some integer. And I'm only going to take the things that are bigger than 0 and less than. So let's say, sorry, I'm going to rewrite this a little bit. This is going to be the set of all x such that x looks like AK plus BL, and 0 is less than x is less than A plus B. Let's just say A. There we go. Less than or equal to A. There we go. That'll work. All right. Why am I looking at this set? Well, this is a set of all things that can be written in this form, and so we would call this a linear combination. A times a number plus B times a number is a linear combination of A and B. So if I can find all of the things that look like that, if I can show that the greatest common divisor is in this set, then I have that the greatest common divisor must look like that. That seems like a roundabout way to prove that it looks like it, but the idea is I'm going to take all the things that look like this that are in between 0 and A, and I have to show this is in here, so I get out this. All right. Well, what I want to do is I want to look at A, and if I look at A, notice that in A, everything has to be between 0 and A. So it has to be strictly bigger than 0. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to A. So what that means is that the cardinality of A, or the number of elements in A, is less than or equal to A. So this is finite. I'm really relying on this whole finite non-empty set thing. The next thing I want to point out is A is equal to A times 1 plus B times 0. So A is in A, hence A is not empty. So what does that mean? That means that A is a finite non-empty set. But what do we know about finite non-empty sets is that they have, well, both the greatest and the smallest element. And the thing we're going to be interested in here is that A has a smallest element. So this set has to have a smallest element. So let's just call that something. So let D be the smallest element of A. What in the world am I doing? If you're asking that, that's a good reason. I haven't even talked about greatest common divisor in a while here. I made some arbitrary setup and I'm doing things. Where is it going? Well, eventually I said that I wanted to show that the greatest common divisor was in this set. I found the smallest element because my goal is actually to prove that the greatest common divisor is equal to D. So that is, if I can prove that this is equal to D, then I get that this has to be in the set, therefore this has to look like this. So I felt like I needed to take a moment here just to remind us where we're going and what we're doing, because we really are going the scenic route here, taking all the country roads. It's a little bit more fun that way in my opinion, but it's hard to keep track of where you're headed sometimes, so I just want to point out where we're headed is, Okay, we wanted to show this, so if we can show that this is in here, we're good. And so we found that this had a smallest element because I want to show these two are equal. All right. So in order to show these two are equal, what I'm going to show is I'm going to show that the greatest common divisor of A and B is less than or equal to D. And I'm going to show that D is less than or equal to the greatest common divisor of A and B. So we said earlier that if we can show A is less than or equal to B is less than or equal to A, they have to be equal. So if we can show this is less than or equal to this, and this is less than or equal to this, then they have to be equal. So we're starting to make progress. The idea is that I have to show that this is less than or equal to this, and this is less than or equal to this, so I get out what I'm looking for. All right. Let's do this one first. So I'll leave that up there. I want to show that this is less than or equal to the smallest element of here. And the way I can do that is I can show that this divides D. Because we said if we can show A divides B, then A is going to be less than or equal to B in absolute value, and both of these are going to be positive numbers. So that would mean the greatest common divisor would be less than or equal to D. So, note, D is equal to A times, let's say, K1 plus B times L1 for K1 and L1 integers. I'm just trying to use different letters. I have K and L up here, so I'm going to use K1 and L1 to say that they're a fixed K1 and L1. Now, we know that the greatest common divisor of A and B divides A. So what we get is A is equal to the greatest common divisor of A and B times, let's say, K2. So that's A times K1 plus, and the greatest common divisor divides B, so that's the greatest common divisor of A and B times L1, or L2, we'll say. So this times an integer is B, and I take B times L1. So I knew that this divided A and this divided B, so I can rewrite A and B in that form. And what I get is I can factor out the greatest common divisor of A and B times, this will be K2, K1 plus L2, L1. Well, K2 and K1 are integers, L2 and L1 are integers. So what that means is the greatest common divisor of A and B times an integer is equal to D. Hence, the greatest common divisor of A and B divides D. And since we've already shown that any divisor is less than or equal to the other in absolute value, and both of these are going to be positive because 0 is less than x, that means that the greatest common divisor of A and B is less than or equal to D. I am so lost. I understand, Fareed. Anywhere in particular you need me to catch you up on, or is it just, it is a difficult proof, and I'm doing this one because it's an important proof, and I know that I'm going to lose some of you. I don't want to lose you too much. I kind of want to keep at least an overview of what we're doing is, I want to show two things are equal, so I'm going to show one's less than the other, and this is less than this. So that's my goal right now, and I wanted to show that this was equal to D, where D was the smallest element of this. So what I have is I let D be the smallest element in here, so I showed that this divides D, therefore this has to be less than or equal to D, so we're almost there. The only thing we have left to do is show that D is less than or equal to the greatest common divisor, and then we get that the greatest common divisor is equal to the smallest element of this set, therefore it's in this set, therefore I can write this as this. Alright, now how will I show that D is less than or equal to this, is I'm going to actually show that D divides A and D divides B. because then if D divides A and D divides B, it's a common divisor of A and B. And since the greatest common divisor is the greatest common divisor, that would imply that D is less than or equal to the greatest common divisor. So the last step of my proof is I have to show D divides A and D divides B. Alright, so that's where I'm going. And so what I want to do is I want to take A and divide by D. Now, if I do that, I know that by the division algorithm, A is going to be some integer times D plus some integer with 0 less than or equal to R less than D. So now we did the division algorithm. The point is that for any two integers A and D, I can say A is an integer times D plus a remainder. So I divide, I get some remainder. The remainder has to be between 0 and D and not equal to D, but it could be equal to 0. Now my goal was to show that D divides A, so what I really want to do is show that R is non-zero. Or R has to be 0. So if R has to be 0, then Q times D is equal to A, so D divides A. Is this all one problem, Danny? Yes. Yes, it is. That's why it's so exciting. All right. Don't try to do it all at once, though. Try to focus on one piece at a time. So just focus on, I'm trying to show D divides A. For right now, ignore everything else, and you can go back to that and rewatch it later. But I'll also give a recap of the entire proof when we're done. But if I want to show that D divides A, I have to show the remainder is 0. So how I'm going to do that is notice that R is equal to A minus Q times D is equal to A minus Q times, I know that D looks like this because it's in the set, so A times K1 plus B times L1. But if I rewrite this, this is A minus QA K1, so this is A times 1 minus QK1 plus, or actually minus, because I have to distribute the negative, BL1. So what that means is that my remainder can also be written in this form. So if R is greater than 0, then R is in A. So R has to be less than D, which here is less than or equal to A. So therefore, if R is greater than 0, it's less than or equal to A, so it has to be in my set A. But if R is greater than 0, it's in this set, and it's smaller than D. Is it possible? Is that possible? Well, remember, D was the smallest element of the set. So therefore, if I have a smaller number in that set, that contradicts that D was the smallest element. So therefore, R cannot be greater than 0 because D was the smallest element of the set, and if R was greater than 0, that contradicts that. Therefore, hence, R is equal to 0. But if R is equal to 0, notice that A is an integer times D, therefore D divides A. So I'll write that over. D divides A. All right. So now what we have is that D divides A. I'm not going to go through this again, but if you start it with B and replace B everywhere there was an A, then what you would get is that D also divides B. Therefore, D divides A and D divides B, so it is a common divisor of A and B. Therefore, it has to be less than or equal to the greatest common divisor of A and B. So D is less than or equal to the greatest common divisor is less than or equal to D, hence they have to be the same number. So if I combine that all together, what I end up with is, the goal was to show that I can write the greatest common divisor of a and b as a times an integer plus b times an integer. To begin with, we had to show that the greatest common divisor existed and was unique. That is, it's a well-defined thing. So I'm not just making stuff up. We found that the greatest common divisor of a and b had to exist and had to be unique. Once we moved on from there, we're then moved on to actually showing the proof or theorem proper was that I can write it as an a times an integer plus b times an integer. In order to do that, I found all of the elements that can be written as a times an integer plus b times an integer that are between 0 and a. I showed that this was a finite non-empty set, therefore there had to be a smallest element. In the end, what I showed was that the greatest common divisor of a and b is indeed the smallest element of this set. But because it is the smallest element of the set, it is in this set. Therefore, this can be written as AK plus BL. Now, notice that was all an existence proof. I wanted to show that there exist integers k and l such that AK plus BL is equal to the greatest common divisor of a and b. So that was a very long, complicated proof with a lot going on. And so what I can hope you can do is, as you're going through this a second or third time, is if you focus on each piece of this had techniques that you can use for your proofs. Saying I have a set and I have a finite non-empty set, so it has the smallest or largest element, is a common thing that we can do to give a proof. Showing that two elements, a is less than or equal to b is less than or equal to a, means that they're equal. That's a common thing we're going to be doing in our proofs. Using our division algorithm has already come up and will come up again in more proofs. So this illustrates a lot of techniques that we can use when we are doing proofs, and it combines them all together to do. We had a contradiction, we had direct proofs, we had all of our proving techniques thus far built into this one really big proof. So this one proof is huge and complicated and hard to follow, but what it does is it illustrates a lot of these. In the smaller pieces, it illustrates an example of a lot of the things you can do when you're working on your proofs. So piece by piece, I feel like this is extremely helpful when you're going through your homework to see, well, how can I use this different technique to get out a proof? And because it illustrates so many different things, that's why I felt it was nice to go through this, even though I'm sure most of you got lost at some point in there. Alright, so you want me to go over why r equals 0? Well, the reason why r equals 0 is a proof by contradiction. I said if r was not 0, it had to be bigger than 0. Therefore, if r was bigger than 0, it looks like a times an integer plus b times an integer. Therefore, it would have to be in this set. But if r is in this set, r is smaller than d, so that contradicts the fact that d was the smallest element of a. So since d was the smallest element of a, r can't be less than d and greater than 0, because that would imply it's in here. Therefore, the only possibility is it has to be equal to 0 so that it doesn't end up in the set, so d remains the smallest element. Alright, anything else in there that I can help you guys with right away? I do have another proof in this section. I might start off next time with it. Something about there exist true irrational numbers, and so it's another type of existence proof where we can show existence without being constructive. But I'm going to actually stop there. That is more than enough for one day. On Thursday, I'm going to start off and I'll go through the homework from this chapter, which if I forget what chapter we're on, to be honest, so I'll have to post that on Blackboard. But I plan on spending the time on Thursday going through some of the homework from this chapter so that we can get some practice with some of the proof stuff. And then if we go through that quickly, I can move on to new stuff. Or if it takes a while, that's fine. We can just do that. So if you guys would look at this chapter, which is the non-conditional proofs chapter, and look at the homework I've assigned on Blackboard and ask me questions, that would be great. Otherwise, thank you for joining me. I really appreciate it. And thank you for all the questions. I do have a question. Is our exam this week or next week? I believe it is next Thursday, but I am going to look it up real quick just to make sure that I'm not lying to you. So mathematical structures. So I'm just going to the website. And your next exam is the 16th, which is next Thursday, as I stated. So that means on Thursday I'll also give you a practice exam. So I'll post that on Blackboard and on the website. And then that means that on Thursday we'll probably be going through homework. So I probably won't do anything new. So on Tuesday we'll do a review for the exam. Yeah, that sounds good. And then I'll give you the exam on Thursday. The exam will be take home, so you'll have until the next Tuesday at midnight to do it. But they'll keep going through it and getting some practice at a time will give you some help with that and something to look back on as you're doing those. We'll talk more about that as we get there, though. Yes, there will be a study guide posted on Thursday. I may get it up sooner, but it'll be up there at least by Thursday. So, and we'll talk more about that on Thursday and then on Tuesday. Any other questions then? Well, thank you guys for being so talkative today. I really appreciate it. I will see you on Thursday then. Have a great day.